Hi, good morning, everyone. Bom dia a todos. Welcome to the 7th International Symposium on Innovation and Technology. I'm Professor Erick, the lead researcher on artificial intelligence at SIINTEC. It's our panel 1 entitled AI for One Ocean, One Earth, and One Health. It's a pleasure to have you all here present with us. Now, I would like to introduce to you our enlightened participants, panelists, Professor Simon C.
Hi.
Hi. Professor Fabio Porto.
Hello, good morning, everyone.
Morning. And the other participant, Professor Alba, but she uh, didn't come yet here. So we are going to keep going on our presentations on our panel, and let's hope that she can attend to our discussion. Okay. So right now, I'd like to follow to our next steps. Well, the our panel will be developed as follows. The order of the presentations will be Professor Simon, then Professor Fabio, then Professor Alba. Okay. So each panelist will have up to 20 minutes for their presentation on the panel's theme. And during the presentations, all the attendees will be able to ask questions through the YouTube transmission. So if you have any comments and questions, please leave it to us in our YouTube transmission through the comments and discussions option and chat option of the YouTube transmission. And after the presentations, we will open the session for questions and discussions. Okay. So having this said, I want to follow to our first panelist, Professor Simon C. Professor Simon C. is currently the Solution Architecture and Engineering Senior Director and Chief Solution Architect and Global Head for NVIDIA AI Technology Center. He is also a professor and Chief Scientific Computing Officer at Shanghai Jiao Tong University, professor in Beijing University of Postal and Telecommunications, and professor at Universitas Indonesia. He is being conferred as a Distinguished Fudan Scholar in September 2018 by Fudan University in Shanghai, China. Previously, Professor C is also the Chief Scientific Computing Advisor for BGI in China and has a position in Nanyang Technological University in Singapore and King Mong Kung University of Technology in Thailand. Professor C is currently involved in a number of smart city projects, especially in Singapore and China. His research interests are in the area of high performance computing, big data, AI, machine learning, computational science, applied mathematics, and simulation methodology. Professor C is also leading some of the AI initiatives in the Asia Pacific. He is a steering committee member of the NSCC's flagship high performance computing conference, Supercomputing Asia, since March 2018. He has published over 200 papers in these areas and has won various awards. Professor C is a fellow member of IEEE, a member of CIAN, IET, and AAAI, and also on the advisory team of AIP AI Professionals Association, and the committee member of more than 50 conferences. Professor C graduated from the University of Salford, United Kingdom, with a PhD in electrical engineering and numerical analysis in 1993. Prior to joining NVIDIA, Dr. C worked for SGI, DSO National Lab of Singapore, IBM, International Simulation Limited in UK, and Sun Microsystems and Oracle. He is also providing consultancy to a number of national research and supercomputing centers. Now that said, I would like to ask Professor Simon to follow to his presentation. Please feel free to
Thank you.
present your nice work right now.
Thank you, Eric. Thanks for the great introduction. Let me share the screen right now. And then right. So thank you again, Eric, for the great for the introduction. And I'm very humbled to be invited to this conference. So my titles for this short little talks basically is AI for Earth Science and City. And the reason why I use city is that basically because one of the things is that at the moment right now, one of the greater challenges in our planet is the building up of cities. So let me get started off. Before I get started, this is the centers that we have across the world, just to give you instructions of our AI technology centers. Over in Brazil, we are collaborating with Professor Erick in SIINTEC, and this is our first centers in Latin America, and we are going forward with a lot of research activities over here. So for those who are interested, could talk to us. Just to get started, the earliest cities that was built was recorded in history is go down to about 4,500 BCs ago, and this is in the city of U, which is in the Mesopotamian regions. Now it takes about almost to 2,900 BCE before there is a consolidated amount of people in one city, and that's 69,000 people, 69,000 people, and that was the largest city at the point in time. Now, over the period of time, as you could see in the 20th century, we have built gigantic mega cities like Tokyo, Shanghai, Calcutta. All these cities are mega cities. They are like almost 20 over million people in one city itself, right? Bigger than some of the nation on this planet. And this give a lot of strains in many things. One of them is that you're going to have resource problems. You have a lot of other constraints, traffic congestion, and whatsoever. And one of the things is that you could see that city right now is making use of artificial intelligence to do city planning, improve the life of the citizens, and so forth. But one of the very important thing is that the cities right now is also causes a lot of problems for the planet. And needless to say, it uses a huge amount of energy, and it generate a lot of heats. In fact, one of the challenges is that living in the city right now, some of the cities can be quite unbearable. In city like Singapore, there is a concerted effort to combine climate modelings together with city planning. Climate modeling, in the sense, is that how the climate is, how the city is going to be designed that is going to adversely affect the climate. And so simulations and artificial intelligence is being used in all aspects. So deep learning is rapidly adopted by Earth science community. As you could see over here, there is extreme weather. We all know about all this extreme weather. I think in Brazil, you guys are also suffering from it. Even in city like Singapore, which Singapore has planned for the city almost like 20 years and 30 years ago to able to handle huge amount of flood. Unfortunately, because of the intensity of the weather right now, a lot of Singapore beginning to experience flooding, even for a modern city like Singapore. To make matter worse, the water levels of the country, of the sea is rising, and this cause humongous problems for Singapore, a country like Singapore and low-lying country like in many other places. And a rise of 2 meters whatsoever will actually take up about 30% to 40% of the island. Now, just go to a background of the Earth science model. We all know about Earth science model. There's a large scale model and then a small scale model. in order for us to understand the planet very well, we need to have some form of large-scale dynamics. Of course, for us to get more accuracy, we need to have some form of long and short wave radiation, or the cloud micros, or the convection layers, turbulence, mountain stress, and so forth, as you can see the list over here. Unfortunately, one of the challenges is that in order to do all this simulation on the large scale dynamics, that require a supercomputer that is beyond our imagination right now. Even the hexascale machines that is proposed could only do a limited amount of the works that we can see. Now, of course, as you guys will know, all these data is coming in from various places, from the satellites, from the data sensors collections, from the oceans, and many other places that we collect upon. Now, just to give you examples, cloud resolving climate models require about 10 million times the performance right now. So if we and to make matter worse, if we want to reduce the time scales to a very small 1 kilometers or below, we require huge amount of computational power, which is almost unaffordable, because no matter how big we build right now, we still were not able to achieve a 10 million times the performance that needed for us to do the kind of simulation. Thus, we have to turn to artificial intelligence, right? Some form of other method, not necessarily just artificial intelligence, but many other methods to do that. So let me just go through a couple of examples. But before that, one of the things is that I guess many of you will know NOAA, which is the world-renowned Centers for Atmospheric Research. They have a artificial intelligence strategy. Basically, you will see over here, there's 4 goals: establish structures and process to advance AI in NOAA, support NOAA missions, accelerate transition of AI research to the application, strengthens, expand AI partnerships, and of course, the air proficiency in the workforce of the climate community. So one of the things that we want to do going forward is to see how can we actually use artificial intelligence to do to emulate some physics, basically some form of fast surrogate models, right? From expensive function that you find inside the computational models of a climate, replace them with a surrogate models of a machine learning models, and then able to reduce the computational time. So these are a couple of examples. One of them is accelerated physics parameters over here. This is basically on a short wave and long wave radiation transfer functions, right? And you could see that, using a form of neural networks, the accuracy, they were able to achieve quite a fair bit of accuracy. At the same time, it have 8 to 10 times the speed up in its calculation. So for one of the module itself, now we can able to speed up to 8 to 10 times. But is that enough? Other things will be, in fact, the emulation of the RRT MGP radiative transfer. And again, no, this is again using neural networks that is able to speed up quite tremendously, as you could see on the graph over here. But more importantly is that we make sure that the surrogate models is very accurate, as you could see on the right-hand side of the screen. Other things will be improve the physics parameterizations. Again, this is basically is a parameterized subgrid process for climate modeling at the range resolutions. So basically is that you can able to compute the mean participation, extreme participation in different latitude and longitude and whatsoever. This has been done by Ginny and Paul Ogoma. And you can find that these papers in Nature. Again, it is and basically the whole idea over here is to build a very accurate physics parameterizations. One of the things is to also do bias corrections. Again, bias correction is very computational heavy, and this is one of the works that NVIDIA, our scientists, is working with ECMWF to remove some of the model bias. And for those who are interested, I will send you the papers over here. But very importantly, over here is that we could, as you could see over there, is that we are able to actually reduce the mean errors to pretty low levels. Now castings, this is again one of the examples that we can now build physical models up to 8 hours. So able to do nowcast and so forth. Now, of course, this is still in the experimental stage. This is done by Google Research in the experimental stage and so forth. But very important thing is now we can build some form of surrogate models to actually helps to do nowcasting in a very quick manner. Now, mid-range weather model, again, this is another one, mid-range models. And needless to say again, this is again for a benchmark test site for data-driven broadcasting. So what the community has done is that they have developed a set of benchmarks basically for people to start experimenting with such technology, machine learning technology, to see how well the thing can be used for weather forecasting. So you could see over here, this is one of the works that done by Stefan and Neurosis, you know, it measures the accuracy of a physical model for a weather bunch. So we are seeing progress in this area. Of course, it yet to be used in the real life weather forecasting, but it can be used at the moment right now. A lot of experiment and a lot of research can be done, and it has shown promising results. Let me just, due to times itself, let me just skip on this. I think one of the very important thing, and I believe our professors later on going to talk about this, is that we could use a machine learning to do very accurate intensity classifications or censorships, right? And again, this is examples of it that we have seen by the works over in the labs over in the US and the universities, the National Hurricane Centers, to able to predict hurricane pretty accurately and in a very quick time. One of the things that we see is that there are sometimes missing climate observations, and using again, you know, this is being done by our scientist David Hall together with his collaborators to fill up some of the gaps, some of the missing data that is not available, and we are able to use some form of gangs to do and together with transfer learning and in painting to beat the other type of algorithms. So the challenges is this. The problem that arise when applying AI to science consists of this. One of them is data labeling. Labeling the data is very, very intensive. There is limited amount of data. Some of the data is limited. There are a lot of other weather data, but some of these data are limited. Now, one of the challenging is that how do we actually enforce a physical constraint? And of course, there are methods like physical informed neural networks. There are also things will be the uncertainty qualification, trustworthiness, and so forth, as the list go down. So with that, I end my presentation. Thank you very much. Eric, back to you.
Okay, thank you so much, Professor Simon, for a valuable time and presentation. And a very important, relevant theme in this area of the use of AI for one Earth, one planet, and one ocean. Thank you so much. Now, I would like to introduce to you Professor Fabio Porto, which is a senior technologist at the National Laboratory of Scientific Computing, LNCC, where he joined in 2009 and founded the DEXL Lab. He holds a master's and PhD degrees from the Department of Informatics at PUC, Rio de Janeiro, We sandwich at Ingria in France in 1996 and 2001, respectively, and a bachelor in mathematics informatics from the State University of Rio de Janeiro in 1987. He was a postdoc at the EPFL in Switzerland from 2004 to 2008. During the period from March to July 2020, Fabio Porto was a visiting professor researcher at the National University of Singapore. Fabio Porto has published more than 100 papers in conferences and journals. His research interests are in big data management, deep learning models, and machine learning management systems. He is currently the coordinator of the CEBD, the National Steering Committee for Database Education and Research. And I thank you so much, Professor Fabio, for your valuable time. And I'd like to give you the word for your presentation. Please go on. It's mute. Your mic is mute.
Thank you, Erick, for the kind introduction, and I greet Professor C and all the participants of this workshop, which I'm very humbled to have been invited to give a short talk and present what we have been doing. Let me just share my screen. It did not appear, did it? Okay, so now it's fine, huh? So you can see the slide. So I will talk about my experience in this extreme weather event forecast, which is actually a recent project initiative that we've been pursuing since last year, but that actually brings the work that we've been doing in weather prediction since mostly 2016, starting in 2016. So, okay. So as Professor C mentioned, is no news that extreme weather events have become more frequent and stronger everywhere in the world, and Brazil is not an exception. And so on the top right picture, you see something that happened a few days ago in Belo Horizonte city. So was a really strong precipitation, 200 millimeters in one hour, which was obviously not foreseen by the meteorologist services in the country. And these are the pictures. This is in the mountain region, in the middle, the mountain region of Rio de Janeiro. And on the left is in the core of the Rio de Janeiro city. So this brings, well, casualties eventually, but a lot of physical property damage and all consequences that we know about that people might associate to climate change and things like that. So this is something that is not to be, is only to be increased in the near future. And this has actually called the attention of the community. Professor Sin already have mentioned the work by Google in nowcasting. So these two papers here on the left are from different groups in Google. Both of them are working with radar images, and but they are from different groups. The one on the top is by the DeepMind research group in UK. And this is in Google Research in the US, down here. And there is also some tracking. Actually, I have a dozen of these different papers being published from 2019 to these days, which shows that there has been an increasing interest in trying to predict these extreme weather events of different forms by using AI technology, AI models. And this is the path we are trying to follow. So the idea is to trying to improve the forecast of extreme weather conditions using deep learning models. And the way we've been looking at, so trying to learn the spatial temporal signals see eventually these events as anomalies in time series, and apply time series analysis, anomaly detection algorithms, and eventually also select spatial temporal prediction models to be applied for those predictions. In the case that you cannot cover the whole spatial area through different, by training models in each of the areas that cover, for instance, the large country as Brazil. So we have been working with this municipality alert services. These are 3 of them: Centro de Operações Rio, Alerta Rio, and Defesa Civil. So these are the main operational services that actually alert the population against extreme weather events. So we're trying to build models that will improve their capacity, the current capacity. And I bring you these pictures, which I found very interesting. This is a study done here in Rio de Janeiro. And what it shows is, so this is for strong rain. So there is these different levels of rain: no rain, weak rain, moderate, strong, and very strong. And when our current models, the models that the alert service currently uses, forecast strong rain, actually only 12% of the cases indeed presented strong rain. In 25%, there was very strong rain, but in 35%, there was no rain at all. So you can already see the challenge, right? When you're talking about very strong rain, then, well, 30% indeed were very strong rain, 30% strong rain, 0 weak, and 63% no rain at all. So if you consider the burden that an alert would cause to the population in this scenario, considering that 63% would not have a single drop of rain in the city, so improving the forecast is very important. This, for instance, this 63% no rain may cause people not trust the alert systems and not actually do what's necessary when the strong rain really will occur. So it's a really important problem that has to be improved in terms of forecast, but again, it's very difficult, right? So we're working in this area, in this regional area of Rio de Janeiro, where you see this square, and one part of the problem has to do with the different kinds of data sources that you might use or modalities to actually interpret what is going on. You can have radar, so we are working on that. So we capture radar data, electromagnetic discharge data, weather stations, pluviometers, satellite images, and numerical simulations, like regional models and global models. Although these are not prepared for extreme weather forecasts. They are usually more for large forecasts, like 4 or 5 days long time period forecasts. But we're trying to combine these different information. Topographic information is also very important. If you see Rio de Janeiro is in the coast, so you have all the effect of the humidity and ocean temperature influencing in the formation of clouds, especially in convective systems. But also you have a chain of mountains which are very close to the seashore. So this eventual evaporation that's caused by convection stops by the mountains that goes up to 800 meters high in a few meters from the shore, and then causing eventually this. And all these hills are packed with forest, urban forest. So there's humidity also involved. So there's a complex system that is put together that we have to try to understand to be able to predict, especially when, where, and how much precipitation we will have. So these are the 3 questions we want to try to answer. Part of the data is spatial temporal. So you see here data coming from satellite images, or time series from weather stations and so on. And so that's why we started with this work here. So that actually was the second work, was a master thesis of Rafael Nascimento, where we proposed this spatial temporal convolution sequence-to-sequence network. So trying to learn the sequence patterns, the sequential patterns that the time series offer, and at the same time learning the spatial correlations through the convolutions model. So that is space and so that is spatial correlation and temporal correlation. So we need spatial temporal models to be able to understand at least the signals that come from more traditional sources like weather stations and pluviometer stations. So this work by Rafaela and us, so we built this 3D convolutional model with a temporal generator block so that we can make the prediction of a certain number of points ahead. So the idea is that here in this first part of temporal blocks, we learn the temporal patterns, and then the input was the information from weather stations in the area of the frame that we are learning. And once the temporal patterns were learned, then we learn sequentially the spatial patterns, and eventually we propagate this in time in the temporal generator block for producing the prediction. So this was kind of applying sequence-to-sequence models to this problem. Before that, we had already worked, that was my PhD student, Jana Soto, where I used the convolution LSTM to actually build an ensemble of post-processing of numerical models. So the idea is that we process we get the output of different numerical models, and then we enter each of the input as a value in a channel of the image, like the frame that we are learning. So, and then again, using convolution and this time LSTM to learn the spatial and temporal correlation. And these results were very interesting. They were better results than each individual model, like somehow dealing with the bias Professor C has mentioned before. So using this AI model to reduce the bias of different individual models, and at the end having improved forecast. Another work that we've been doing is this disjoint ensemble, and the disjoint ensemble, the idea is to, okay, so if I have a large area to predict, and all those convolutions models are learned in certain frame, which are reduced size areas, you're probably not going to be able to learn models in all the surface of the country in Brazil. So there is no sense of doing that. So, but if you have already learned parts of Brazil, can you use these learned models in areas where you have not learned, where you don't have a trained model? So how do you compute the best models, and how do you combine the models you have so that you have a good prediction in areas where you don't have any trained model? So we use data analysis, but you use information about the data distribution in different regions. So for instance, getting data from meteorological stations and computing the distance between the areas where the training occur and the areas where you want predictions to be produced. And by computing the distance, we estimate how good the models learned in one area would fit to another area that they have not seen. So this disjoint ensemble put together models so that we can cover areas that have been not covered previously in training. And to do that automatically, we have developed the GYPSY system. So GYPSY system is an AI model management system that intends to do various things. So this is a general architecture of the system. And the idea is that it can, for instance, compute automatically these ensembles given a query. So SAVIMI is another system, is a multidimensional array query system that we have developed. So you can query for predictions in a certain spatial time region, and this query is automatically selecting models that are registered in Gypsy to answer the predictions that we want. And we can run this in supercomputers, or you can run this in like Spark-like architecture. So this is a front end to the scheduling and the automatic selection of models so that we can provide the alert service at the end, the users with better predictions. So finishing my quick talk, these are techniques. So we are starting in this extreme weather. So we are very interested in now. We have already a first result in the master thesis of Thiago Moeda that I didn't show here that uses a self-organizing map and LSTM for depicting extreme weather as anomaly detection strategies. We're also looking at deep learning models based on radar data. This is something that is being done, as I mentioned. We want to learn this and see how to process efficiently radar data. And we are increasingly building Gypsy systems so that transparently all these decisions in how which model selection of models to apply and optimization of these selections can be done so that a user can have the forecast in better quality. And I finish my intervention at this point. Thank you very much, and I'm open to questions. Thank you.
Thank you, Professor Fabio, for your nice talk and presentation. Very good presentations from you guys. I am really appreciating it. Very interesting points and contributions. Well, as you know, I am very familiar with this theme and weather forecasting using numerical weather prediction models and also AI deep learning models. So it's very delightful to me to listen to you talking about some very important and relevant topics. Well, we have some questions from our public, from Risieri Pedruzzi. The question is, VI application meteorological modeling correct and bring the modeled result towards the observed learned data from the AI, correct? Wouldn't this approach interfere in the mass conservation? Well, I think Risieri is worried about is questioning how AI would be able to learn from data information regarding, for example, mass conservation and other physical properties from of the atmospheric fluid of the air, for example, for weather prediction. So, what do you think?
So let me try to answer this and correct me if I'm wrong. So I think one of the approach that some of the researcher is taking on right now is what we call physics-informed neural network. So it can be combined together with data-driven neural network, and basically the whole idea about physics-informed is that you think of it as is that the neural networks, the training of the neural networks is constrained by the physics, which is described in partial differential equations or any form of things on that. So you have a neural network going through, and then you're able to compute the necessary derivative, and then you do the and then you're being constrained by the equations, for example, like mass conservations or whatsoever, and then and provide the feedbacks into the results and to provide the necessary results, right? So this is one of the ways to actually go about doing it. There are other approach where other people have taken on, where, for examples, where the people will be using neural Fourier operator, and then again the same thing. You do have to do describe the entire equation, basically model entire equations into using a neural network, but replace it with a Fourier neural operator. And then from there, you can actually find a way to constrain whatever physicals constraint that you want to put it on. So this is some of the approach that's been taken.
Oh, very nice.
Yes, I can comment on that. Well, I'm not a physicist, but so we have been working with meteorologists from USP, Universidade de São Paulo, and so one of the questions we are trying to answer is whether or not AI models can really substitute numerical models, and to which extent in the reproduction of this physical phenomena. And so we did do an experiment where we have a numerical model of a very simple closed system, like imagine a bowl and some point in the middle, some strength being placed in the middle of this bowl filled of water, and then it produces like waves that ripples through the borders and then reflect and come back again. So you're trying to simulate the sinusoidal model in this very closed and simplistic environment, and using the architectures we had so far. So this we look working on this convolution S2S model that I referred to in my talk, and so the idea then was to apply, as Professor C, constraints on the loss function regarding to the mass conservation, and see whether this would improve the reproduction of the phenomenon. And well, indeed it did, but was not that as good as we have expected at that point. So it's true that we want mass conservation as to be seen as a constraint on the physical system, and this can be done. And one of the ways that people are doing that is to add this penalizing your loss function with these constraints that you extract from the physical world. And we've done this, so I'm just reporting here experiments we've done, we have been doing. We haven't yet conclusive results that have been, especially, so we start with good results, then the periodicity of our waves start to degrade. And we haven't been able to really have good results on that. But yes, I think the general comment is that by adding constraints, we expect to improve by optimizing, so reducing the time. So why do you want to do that? I mean, that is one thing that I should mention, is that we want to be able to produce numerical simulations of very high frequencies become very expensive to do so. But in AI models, it doesn't. It's very cheap to produce iterations forward on AI models. So the question is this frequency augmentation equipped with good quality prevision? And trying to answer that by adding physical constraints that maintain the forecasting good quality. So this is what we're trying to do.
Very nice, very interesting. So another question is from Diogo Ramos. He's asking how the climate change scenarios can difficult an AI strategy for weather climate forecasting, considering that historical data are more and more different of actual observations. What do you think? I think it's very related to the first question. I'm just trying to not interrupt you and not bring my comments, but because the people would like to hear from you, not from me. So, but I have some very interesting opinions about this. But please, what do you think about the Diogo Ramos question?
Well, I can take. So this is another area that we've been working on, is what's called detection of concept drifts. This is one of the ways that you can combat variations on the trend of time series by more dynamic models. So a problem that we have currently that's related to your comment, Diogo, is that models are static in the sense, traditional models, AI models have been static in the sense that they learn the patterns that they extract from the data you have, in this case, the historical data of weather climate, and they don't change. So the predictions follow this, what's being learned. And if the patterns change, then you start having worse predictions, right? So one way to combat that in one area is try to first realize that you're producing wrong predictions. And this can be done in two areas, either in the input. So you see that the data distribution input is different from the one that you have observed. So this is already something good, because you can use simpler models, but cheaper models to train and respond while you keep the time needed to retrain your model. So to give you a practical example, we can use weaker models like ARIMA, kind of auto-regression models for time series, and having them trained as the new data comes. If you have understood that the trend that you've learned has changed, while you change your main model. This is one way to do it. Another thing that we have been working also is in incremental models. And what is an incremental model is? So if you have learned some, and this is more done in classification problems, and not in regression. So classification problem, you can see, well, let's classify if this is an extreme or is a normal weather condition. So you have these two classes of problems, let's say. So now you have an extreme new class that you haven't seen yet. A third class, which you would classify as something extreme. Now, if your model was trained to classify into these two different classes, how are you able to extend incrementally your model to now classify extreme conditions? So we have just sent a paper on that, on this incremental learning, where you freeze the penultimate layer of your network, and you can analytically compute the classifications that will go in a metric space in a different area. So we use metrical learning for that, and extend the metric space to new classes. So I think in general, the idea is to build tools to dynamically react to what you're observing. So this is one way to go, I believe.
Great. Professor Simon, do you have any contributions on that?
No, this is the extremely challenging problems, because like what Professor Porto has said, what the neural network learn is, and from a mathematician point of view, is that what we are trained the neural network is that we train it within that particular space, and anything that we are trying to move out of the space, it become challenging and unstable, right? So there are different techniques like what Professor Porto have says, and people are experimenting with that. We are trying to see what are other techniques that can be used to actually able to project out of that particular space. I mean, we can do, there are neural network, for example, like some of these regression techniques whatsoever, you can actually project out with a limited amount of things that outside the space. You could actually step out for a short while, but you cannot project it too far off, and that is basically one of the challenges, right? Because neural network is based on that, and there's a reason. I think that is also the reason why the simulation itself, the basic simulation modeling models, is not going away, because that will be that will contain all the necessary physics that's contained inside it. It's just that some of these models is going to be replaced by a machine learning algorithms. It's surrogate models, right? And then you still have to run through the simulation to actually predict what is going to be in the future. And that's how I see and many people are seeing that. So it's not a total replacement of a neural networks that are going to replace the prediction models. It's going to work hand in hand together with simulation models.
Great. I'm trying to keep silent during these discussions, but it's almost impossible. Well, I would like to. We don't have any questions from our attendees, but I'd like to bring two questions for you. It's difficult to join such a great people in one talk, so let's give this opportunity. Well, I'd like to know from you, what do you think, how do you think AI and numerical weather prediction models can be combined together for the task of weather forecasting? Well, Fabio Porto already presented some strategies for this. Okay, for example, using output from numerical weather prediction models and training some ensemble weak learners, maybe producing a stronger learner from those weak learners based on the output of numerical weather prediction models. This is a strategy. And we also have opportunities to use graph neural networks or spatial correlated spatial evolution, temporal evolution approach, like one of Porto said. But how do you think, on practical terms, numerical weather prediction models and AI can be combined together for improving weather forecastings? Because, as you know, we can use it for several areas that uses numerical weather prediction, that use weather forecasting results. For example, in renewable energy sector, smart cities, and so on. So, what do you think?
Well, I think Professor Porto has described quite a lot of very good strategy that's going ahead, and I think one of the things is that at the moment right now, a lot of these things are still in the experimental stage. We are still trying to. I think if I understand correctly, Professor Porto may correct me if I'm wrong, is that the community are still experimenting with various approaches to see how can they actual fact have a able to predict it accurately, right? And accurate, not just accurately, but also able to compute it in real time.
Yeah,
right. That is one of the biggest challenges, is that when we want to get more accurate, we have reduced the grid size, and that basically explode the amount of space that we need to compute. So there's a bigger challenge, and the various approaches that Professor Porto has mentioned is there is some success over there, and people are still experimenting to do that. I'm not that sure whether is there any other new approach. I believe that there's some other new approaches that people will be suggesting going into the future.
Nice.
Yes, I think that's really the challenge. And so our colleagues, for instance, in the alert system in Rio, would like to have predictions in the scale of 300 meters, in a grid of 300 meters. So it's for numerical methods would be very challenging.
Right.
And also, and that's what we're looking for, radar information, because also if you get, for instance, talking about AI models, so we don't have weather stations covering all the area that we want to predict. In Rio de Janeiro, for instance, is a very sparse distribution of points in space. And this calls to what Erick mentioned. So one of the things we're trying, so I link into another issue than your question, but just to complement, is that, so we have this problem, for instance, for weather stations, we have this scattered in some points in the state, and then we're using graph models to try to interpolate that, or extrapolate that to the regions where we do not have the stations measuring the actual measurements. So if you want to train a model, and a model uses like a frame, you need to have like a grid, and this grid might in one side be in a smaller scale. Then you have the meteorology stations distribution, but also you might have huge areas where you don't have any measurement at all. So you must be able also to extrapolate the information from what you have to the regions where you don't have, so that you can train your model. So, and so there is all these challenges on doing that. And then, so we want to juxtapose, for instance, radar information on that, so that covers really the region with the current, the moment data. So yeah, I don't have a good answer for that, rather than what we have mentioned before, of combining models and doing this post-processing that we'll be doing. And so while I was in Singapore, there was a colleague in my room that was working in this idea of adding constraints to the loss function. So this is one way that people have doing this physical informed neural networks, and that's what we've been doing in the example that I discussed before. But it's very premature, so we don't know exactly where this goes.
Okay. Another new, pretty new area, new approach, which is still in its very early stage, and this is basically created by my colleagues over in Caltech, Professor Anami and her students, is something called the neural Fourier operator, right? And basically, the whole idea is that the entire equation is replaced by the neural Fourier operator. However, the good thing is that operator become basically grid independent, so it can actually simulate it. You can actually do simulation with various grid size almost independently. The problem with it is that it requires a lot of training data in order to train it. So for a numerical models, weather numerical models, to generate out the require the number of episodial data in order to train that things may be quite daunting, right? But if we and that is something that we actually could have explore on how to use that new techniques that is came out from Caltech.
Very nice, very nice. Thank you so much. And one last question, this discussion brings me to this last question. Well, as I think Porto mentioned about it, that recently DeepMind got big attention on its AI that is able to predict almost exactly when and where it's going to rain in UK. They trained it again-like model using radar data, and released it every 5 minutes. Those radar data are released every 5 minutes. With better results than state-of-the-art numerical weather prediction models for the next 90 minutes. So the question is, why do you think it gained so much success in comparison with NWP models?
I don't know the answer, but I
in
don't
your
know.
opinion, feel free to comment.
No, but what I can say is something that we have been looking and is related to that. It might not have any relation to the success of this model, but something that we're looking at is that, so the work that we've been doing until now would learn the time series in each point. So basically, you get the frame in the spatial area, and you have the time series, and you learn that. But my suspicion, one thing that we're looking at now, is that to identify where and how much, what the quantity of precipitation we will have, you need to learn the dynamics of the phenomenon. And the dynamics of the phenomenon means how how is the clouds that are forming are going to evolve through time and space, and where is going to actually fall in very extreme patterns. So to do that, one of the suspicions we have is that we should learn horizontally and not vertically the data. So that means that, for instance, you can get the nucleus of the cloud formation and try to build the trajectory to the radar information that this nucleus is developing through space and time. So it's like we would learning the trajectory of the cloud's nucleus through the city. And so that we learn the dynamic of the movement, and then with that, we can be able to define where actually will the extreme weather occur. Because it might rain like 10 millimeters here in my place, and then we don't care about it. But later on, it may fall in 200 millimeters in the other side of the city, due to the same nucleus of set of clouds. So we should have learned why was the case that this phenomenon started in one region, for instance, close to the shore, and somehow moved in between the city and eventually collapsed in a certain area. So one thing that we're trying to, so when you look the images from radar, you usually see a video, right? You see a video where you see this nucleus moving in different colors depending on the density of the humidity and electrical discharge through the space. So let's try to learn that. So I'm learning trajectories that you would learn trajectory of a person walking the streets with her cell phone. Can we do the same for clouds? And then identify these dynamics, and eventually the dynamics would lead to the when, to the where part of the question, and eventually the how much rain as well. But this is, by the way, the paper that I mentioned, tracking hurricanes, they do something like that. They do that, something like that for hurricanes that we can follow with easier way. So, yeah.
Okay. Oh, nice, very nice. Well, I think we have no other questions from our public. Well, it was a pleasure, a really pleasure from me and for us and SIINTEC to have you both here participating in this panel with the theme of AI for one planet, one ocean, and one health. Thank you so much. Simon, what time is it now in Singapore?
It's 10:30 in the evening.
10:30.
Oh my God, so sorry to bother you.
Oh, not at all. The pleasure is all mine. The pleasure is all mine. It's
I was there in the beginning of the pandemic on March, between March and July. Yeah.
Yeah.
Very nice place. Yeah.
I'm planning to know Singapore, maybe after the pandemic situation, and visit Simon there.
Yes, definitely. It will be. I'll be definitely welcome you guys to come over to Singapore, and then we should have a face-to-face discussion about this topic.
Yeah, very nice.
That would be great.
And we are going to have our discussion next week, right, Simon, about this very topic. Very nice. Yes. Well, thank you so much. So Fabio, please.
No, I would just thank you for the invitation and this nice atmosphere, and thank you, Simon. It was a pleasure to meet you, and Erick, again, as always, a very pleasure to share some time with you and share our ideas. Thank you very much.
Thank you.
Thank you. So let's give a bye-bye for everyone, and hope to see you soon. Bye-bye.
Okay, bye-bye.
See you soon. Bye.
Bye.
Bye.